everybody. My name is George, and today I'll tell you something about efficient LLM agents. Well, first of all, who am I? I am a researcher at Yandex Research. I do some stuff related to LLM efficiency, some inference tricks, safety, interpretability, somewhere around that field. So I'm finding myself in. I'm also a lecturer at NLP course at YSDA. Some of you may know about this fancy place. Yeah, if you have any questions afterwards or just want to talk, here's my Telegram, just in case. Okay, so what's efficient LLM agents? We are not going to talk about efficiency of LLM, so no inference stuff, no pre-training stuff, no kernels, no kind of this stuff. But the area that is, well, efficient LLM agents, I think is a little bit underexplored in terms of, well, academia and production settings. But, well, I guess it depends on the use case. The idea is as follows. You have some task where some latency, well, between the user input and output the system gives you is something that is important, and you want to reduce it. There are a lot of cases where it can be applied, but the common thing among all of them is that you do not want to change the model's insides. You don't want to use more efficient kernels or whatever, because it's kind of the idealistic tricks where you want to use KV cache in some certain unusual ways to reduce those latencies or other kind of times that you want to optimize. It will be a little bit clearer on the examples. But before that, I want to quickly go through the transformer recap. I think that most of you know all of this stuff, but some of them will be important in understanding of the mechanism later. So we'll go through that quickly. Well, we know each other. This is transformer. Attention, MLB stuff. Well, nothing crazy. The question here is the interaction between tokens is hidden inside the attention mechanism, and that's important. We are not going to talk about linear attention here, but I can answer in questions afterwards about this kind of stuff. And by the way, if you have any questions on the way, please go ahead and ask it when they appear, and don't wait till the end of the lecture, please. I think it's should be more of a dialogue than one-way data transfer. Yeah, and the way the autoregressive models work, they use casual masking, so nothing special here. It is not that important, but still nice to remember. The order of tokens is what interests me the most here, and let's do some interactions. Can someone tell me which way the transformer incorporates positional information of tokens inside the transformer? Okay, 9 a.m. it is. So rotary positional encodings, they are applied inside the attention. They they rotate queries and keys by a certain angle that is dependent only on the position of the token, and you get some beautiful pictures where depending on the position, the vector is rotated in some capacity. Okay, so you probably know that. The last thing I want to recap here is KV caching. That is also important stuff. It reduces memory usage on inference drastically, and those stored KV vectors will be very useful in our later talk today. So yeah, if you didn't know how KV cache works, you just look at the picture and understand it. Did something happen? Okay. Let's start simple. Well, one of the cases where you can use LLM agents more efficiently is when you want to optimize the long output of reasoning traces. So the task is pretty simple. You have a, for example, math question, and to answer it, LLM usually outputs a lot of tokens, like reasoning tokens, to do these, that, and whatever for long periods of time. This, you can view this as kind of a tool of LLMs, well, not in a way IP calls are tools, but in a way, well, just a thing that helps LLM output certain final answer. And inside those traces, there might be sequences of tokens that are parallel by design. So a question may contain some certain cases, case A, case B, for example, which are independent of each other. Or the solution may imply some different well, approaches to the task, and LM could potentially explore both of them, but is forced to choose either one or the other, well, before knowing which one is correct or a more simpler one. And that inherent task parallelism can be explored to, well, reduce the time needed before LM agent outputs the answer. And that's where I think you may start to see where the efficiency lies. So it's not about how fast model works. It's about how fast we can, well, manage context or employ some inherent task, well, dependencies or architecture inside like the task as a whole to reduce the time needed before you see the answer. So let's look at some prior works. More naive approaches here may use some simple multi-agent setups where, well, either you launch the LLM with full chain of thought and reasoning process a few times and somehow choose the final one, either by, well, just finding the answer which is the most popular among the agents, or well, launching the multi-agent debate is where when you launch them, well, a few agents, they output some answers, they discuss them among each other a few times, and while they and when they all land on the same answer, you, well, output it. These are not very efficient, you may guess, because you need to solve this task a few times before you can output the answer. So it may increase the accuracy on some math tasks, but it does not reduce the time, which is a problem we are trying to solve. And more elaborate schemes that can, well, help with this are skeleton of thought and pasta. A skeleton of thought, firstly, gives you a plan how to solve this task. So you do this, that, and something else. And some of these may be done in parallel. For example, one agent explores one direction, the other explores another. And, well, after all of them are finished, the first agent aggregates the results and outputs the answer. You may see the problem here is that it is not flexible at all. So it still lags in terms of efficiency when one of the traces appears to be more time-consuming than the other. So you may have a simple case, you may have a harder case, and you're bound to well, harder case time when solving the whole problem. And that is something to consider in designing our, well, approach. Pasta is something else you well, LLM can call some async kind of forking itself into well, solving smaller cases. So you have a reasoning trace, and you want to solve some equation. And you just ask your subagent to do that while you reason for something else. But the problem here is the same. While you can call those forks at any time, you still have to wait till they finish. And they may be time consuming, and well, the whole system is a little bit hard to engineer to work properly. And yeah, so these are some ideas on how people try to, well, improve the efficiency of these agents. And now I want to present you our previous year NeurIP submission, which got, I think it's Spotlight, yeah, on the NeurIPS 2035, which is Hawk-Wild inference. And yeah, what's that? It's modified inference for LLMs, so no additional training required, which heavily uses the roping mechanism and KV cache to do some trick which allows a lot of stuff to happen. Let's start with the simple, well, idea that we want to have a few agents, for example, Alice and Bob, which are solving the problem you are given in parallel. The expected behavior is for them to cooperate with each other while seeing each other's outputs in real time. You can imagine it as if you are working in a shared Google Doc. You're writing some stuff in it, and your friend sees your writing in real time. That potentially may improve your efficiency, well, in writing solution, or may not. It depends on your ability to collaborate with each other. And to do that, we introduce, well, cache block. That's, well, block of KV cache that can have the KV stored inside of them for Alice, Bob, and maybe something else separately. And new incoming tokens and KV, new KV vectors can be stored inside of them. And by running the forward pass in batch for, well, Alice on the index 0, Bob on the index 1 on the batch access, you can have two newer tokens for Alice and Bob respectively, using just one forward pass. And then using some inference trick, you can make them appear for Alice's perspective in order common cache, Bob's cache, Alice's cache. And then this part of batch will generate Alice's token. And for Bob, you can arrange them in a different order, well, common Alice, Bob, and the output will be Bob's token. What's the idea? The idea is to, well, remember that the only thing that defines the order inside the transformer is rope encodings, and those can be manipulated using, well, simple rotation mechanisms. Let's store all of our cache inside of cache blocks in, well, ascending order, but with offset of 0. So in the common cache, there is position 0, 1, 2, 3, etc. For Bob, it's 0, 1, 2, 3, etc. And for Alice, the same. And inside the attention kernel, let's duplicate the incoming query and rotate it by, well, corresponding angle, depending on the lengths of the, well, blocks of cache combined. So the resulting dot product will be equivalent as if the cache blocks were rotated in the right place. I think that's the core idea. If you have any questions here, it's better to ask them right now. Okay, let's move on. So the results of this trick is that we can have multiple cache blocks that correspond to some parts of context that we now can move in inference time between forward passes. So on one forward pass, we can have, Alice generate its new token. For Bob, we can have, or for another forward pass, we can have only Bob generate a new token. Or, well, in batch, they can simultaneously generate tokens for each other and synchronize, well, each forward pass while seeing each other's tokens, well, in real time. Yeah. So how do we make them collaborate? That's a good question because, well, while you try to run this setup without anything, you just make both of them a little bit confused, and they try to solve the task on their own. While adding a simple prompt, I think you can see, but it's something about, okay, there are a few of them. One of you is, well, Alice, and this is, well, a main. It is your thread. You are writing your thoughts here, but you can see the thoughts of other agents above. And well, to increase the collaborativeness of those agents, we insert every 1,000 tokens this simple quote: "Am I doing redundant work? Yes or no?" Well, that is inspired by some previous works in reasoning. While inserting something, and well, every one key steps can change the behavior of an LLM. So in here, this helps the, well, this helps. We'll see this on the graph on the right. The interesting part here is that agents sometimes answer interesting things on this question: am I doing redundant work? The funniest thing we've met is, am I doing redundant work? Yes, but that's okay. Well, hard to argue with that. So how to look at this graph? You have an up. I presume do not look at the graph. Okay. You have a baseline, which is model tries to well, solve the task regularly. Well, one agent, one forward pass per, well, forward pass, one token per forward pass. And we restrict the budget for tokens generated by the, well, power of 2. Oh no, it's not power of 2, but okay, so thousands of tokens. And this one is 16K tokens baseline generation. You can look at Hogwild, that is orange line, which is a little bit upper overall, and some other variants which are not that important, except the yellow one, which is without that collaborativeness prompt, which, yeah, is worse at every point than the baseline. How to look at this graph? So if you want to compare two lines, you can see like that the accuracy for the fixed budget is, well, higher. That means that, well, if you want to achieve the same accuracy with less budget, you want to choose the higher curve. What does that mean? That means that we can achieve higher accuracies with less forward passes. And that is a proxy metric for how efficient our LLM agent is. But, well we'll need a further testing for, wall clock time. We'll look at that a little bit later. Okay. One other thing is maybe accuracy increases, with fewer budgets. But how do we measure? Well, we can look at the traces and try to see if those are, collaborative or not. We try to use LLM as a judge and provide them with 6 levels of collaborativeness, where 1 corresponds to no collaboration at all, 6 correspond to, beautiful, super parallel, efficient collaboration, and, measured the collaborativeness of some subset of reasoning traces. And we actually can see that the more frequent updates are, by the way, those are different setups when the synchronization of, output tokens for Alice and Bob happen either every forward pass or in certain scenarios where the LLM agent finished its partial thought with /n/n. Okay. This setup is easily scalable for more workers. When you have like Alice, Bob, and Charlie, I don't remember, Dan, I think we call them. So, you can guess the namings. But the idea is this is Qwen 332b, or yeah, something like that. And the idea is that the more workers you have, the more accuracy you get per same budget of forward passes, which is cool. There is some abnormal behavior on the 6th worker, but that is caused by, context limitation of the model. We can see the same trends on different benchmarks for math, for physics. Heavily dependent on reasoning benchmarks. The LifeCode bench, IMEA, which are all, by the way, done with QVQ 32b, 235b, big Qwen. Yeah. Here is the LLM efficiency stuff that we are also interested in, because if our custom implementation of that inference trick is not efficient, then running just 2 forward passes, maybe it just doesn't make sense, which is not which is not, you can see that the, for example, tokens per second is almost twice for 2 workers, and, closer to 4 times, around 3 times and a half for 4 workers scenario. So it's not inefficient, and it's close to, given 2 times more throughput with this setup, while providing collaborativeness between the workers. This is demo, by the way. I think it's very cool, and I think you can see that from anywhere. The problem is to find the function in 4 points, and then Alice and Bob collaborate in real time, trying to first of all split the task into 2 independent chunks, and they change their plan on the fly, while Alice first introduces 1 and 7, and then changes to 6 and 7, while seeing the Bob taking the other 2. I think that's cool. And the cool part of it is that it's happening training free without any additional model modifications. And the only thing you need is to have full attention layers and well, be able to run the custom inference track. There are works, for example, Paralleller1, that, well, does something akin to SFT plus RL on, well, some setups, which is close to trainable hog-wild inference, but, well, not exactly the same. And it achieves, well, some results on the benchmarks and gives some idea that this is the thing where LLMs can improve, giving the budget for training and, well, some interesting stuff with inference. The next thing I want to talk about is responsiveness. It's, well, kind of related to the previous stuff. So previous one was parallel reasoning. Well, you have a big reasoning trace and you want to finish it earlier. Now you want to give an answer earlier. That's a little bit different of a task. Parallel reasoning is, well, you want to finish reasoning. And now you do not exactly want to finish reasoning. You just want to give an answer earlier. So the same problem, the same, well, idea of long reasoning traces, but now you want to give an answer. Well, not as early as possible, but, well, still correct answer, but as early as possible. To measure that, you may, well, first instinct is, for example, time to first token, which is a common metric in these kind of scenarios. But as we'll see a little bit later, this is not like a very good metric. We use silence, well, measured by TTS, some TTS run over the output traces of the model, and measure the total silence time, well, in pauses, because our method will output some pauses as well. You'll see. Before that, there was a few works that I want to highlight here, one of which is Pontaine. It's the paper from Google. No code, no nothing provided, just an idea. So here it is. They train model to output chunks of output before giving the final answer. So you're going to have a plan which can be rejected with additional user inputs or accepted with additional user inputs. Then you have like a thinking phase, which is not visible for the user, and then you have the response. This is a strict, well, pipeline of giving the answer, but it gives an LLM an opportunity to give a partial answer, receive the feedback from the user, and then proceed with, well, giving the final answer. This is another paper of ours, which is, well, on this responsiveness topic, which utilizes the similar trick. Well, let's highlight the higher overview first. So we have a task, and we want to think about it, but at the same time give the answer quicker. So let's have two, well, instances of LLM, like thinker and writer, instead of Alice and Bob as we had in hog-wild. And thinker will, well, think, generate reasoning tokens continuously, while writer sometimes will look at the thinker and decide, okay, now that's enough for me to give some partial answer. Let's do exactly that. And in those chunks, writer can generate answers while reducing the, well, latency between the query and response, and, well, in that way increase kind of efficiency of this LLM agent. This is more text than it was before, but the idea is the same. We have cache blocks, and, well, we have a common cache at the top. Then thinker, well, let's start with writer. Writer sees thinkers block current output as its own thoughts in reasoning trace. And then you have a writer's block which generates the output while it will be converted to the speech afterwards to give the user online output. And the thinker, it may depend on the setup. In one of the setups, it may see the writer's output as a previous turn. So that is one way to look at it. The other thing is to ignore that part completely and utilize the trick I'll tell you a little bit later. So the idea is the same. We have cache blocks, we rearrange them, but now they are not symmetrical as they were in Alice and Bob scenario. And one of them corresponds to thinking and the other corresponds to writing. And that reduces the latency. You can see the familiar picture here. There are a few engineering tricks we've made between those iterations. One is support masking for, we have asymmetrical cache blocks, asymmetrical agents. So now we have asymmetrical prompts for them. And that is something to consider, as well as being able to run thinker only on one forward pass, and then both thinker and writer on the other pass. Otherwise, the idea is the same. We have stored cache blocks with a set of 0. If we want to use them in some order, in some view, we duplicate incoming queries, rotate them, and multiply by the corresponding KV cache blocks to achieve the mathematically equivalent computation. The trick I was talking about is mode switching. So instead of giving the thinker the whole additional turn in its context of writer, we can use this simple question as the other, view. What's view? The order of cache blocks is view. So we can add another fourth cache block with that, with this question. Wait, are my current thoughts enough to write the next paragraph? We can ask the model on, any forward pass in the batch, third instance of batch or second instance of batch, if you, are running the thinker and writer in parallel. And arrange the blocks in prompt, writer, thinker, and then mode switching question. What that will do is, ask the model this question, and using the probabilities in the output of that forward pass, you can determine, do you want to activate writer right now, or you want to just fall back to thinking a little bit more. And that's the main setup we use in all of our next experiments. Let's look at the graph. These 2 points are baselines, one of which is thinking baseline. The other is not thinking baseline. I think the names are enough to introduce them. The other dots are interleaved thinking, is when you kind of simulate that behavior of ours with thinking and writer, but with less efficient time, less efficient implementation, where you see that it reduces delays substantially, but an accuracy drops as well. Dear is early exit. There are a few methods that provide non-trainable, mathematically determined criteria to stop reasoning at this point and give an answer. So early exit, early stopping, as you can call it. The idea is every few tokens, you launch a forward path with, okay, that's enough, the final answer is, and measure the confidence of model's output. And if it exceeds some predetermined threshold, you just end the generation there, and that's enough. That gives like moderate delays while having smaller accuracy. And the last one is thing switcher is, well, it's an additional criteria that is trained on some data to, that looks at the incoming query and decides, do we want to use this strategy, so non-thinking strategy, or thinking strategy, based on the incoming query or the common task alone. And on average, that gives, higher delays but higher accuracies, while our async reasoning setup, with a few variations of those, can have the delays that are closer to non-thinking while achieving accuracy of thinking baselines. Yeah, these are some graphs for Qwen. We've primarily measured this setup on Qwen family of models with some other like GPT-OSS, GPT-OSS models, yeah. The idea is as follows. We measure, so here is accuracy only plotted, I think. Yeah, I don't see any delays, but for different benchmarks. And for the for other models, here is more stronger models, harder benchmarks. And if you see here, you can have accuracies which are closer to thinking baselines than to the interactive, which is non-thinking baselines, and delays which are higher than an interactive baseline, but much lower than in the delays. The caveat that you may find here is that one strategy for the model to reduce its total delay, which is measured in total silence time of the output TTS output, is to generate gibberish or nonsensical outputs, just to fill the gaps between the meaningful states. But first of all, there is no training pressure, optimization pressure, because there is no training involved here. So the model does not train to fill those gaps, and that doesn't happen usually. And you can look at the number of generated writers generated tokens and see that they are a substantially smaller number of those than the generated reasoning tokens like thinker tokens. You can use that trick of rearranging thinker and writer to boost the safety of the model, because it is for regular models, for example, for regular reasoning models, for baseline thinking here, is something where in reasoning traces, something may happen that will steer the model to comply with users' harmful request. For example, the model can, kind of gaslight itself into thinking, okay, it's like just for studying, it's a hypothetical scenario or whatever, and output the compliant output, which is actually harmful. That's why you can see the attack success rate on the thinking models sometimes may be larger than or non-thinking model which see harmful requests and do not comply. But that can be resolved with some safety prompting, which drops the attack success rate almost to 0. That's usually what is used in production scenarios in, well, serving closed source models, when the model is provided with some big chunk of text which explains why you should not answer harmful requests. And yeah, that pretty much always protects the model. But this scenario is not interactive, and you cannot have a lot of reasoning, a lot of time to think about how harmful the request is, and at the same time have the lower latencies on the interactive scenarios. One which can be, well, a speaker. Well, I think around half of you may know the Alice assistant, or any other similar agent that should be interactive. You want to speak to the thing and receive an answer earlier, rather than wait for like 5 minutes for it to say, okay, the weather today is whatever. Yeah, and running our setup with safety prompting and without it can give you, first of all, the closer to baseline accuracies, which is what we've been doing, reduced latency, and preserve, with additional safety prompting, lower attack success rate numbers, which means that the model can certainly think and stop itself from giving harmful outputs before finishing the generation. One additional thing that I want to talk here about is additional human inputs. That's a very interesting scenario where, well, you have, imagine a speaker, you talk to the agent, and you ask for, I don't know, give me, well, the weather, for example, in whatever city. It starts some API call to like weather website or whatever, and starts thinking about it. For example, I don't know, it's looking at your schedule, determining your well, plans for the day, and then you decide you want the weather not in your city but for your friend in another country. And well, first of all, the usual behavior at this point is to stop the generation and start from the beginning. And maybe in that case I just generated for you is the most correct option, actually. But for some tasks, for example, for generating the, well, asking for the script, that does something. And then you decide that you want it for Windows operating system, not the Linux, like generally considered, well, the default standard. And while thinking about the script and how it should be done, there are some useful thoughts maybe already being generated, and stopping the generation and starting from the beginning may be, well, wasteful in terms of spent compute. So instead of stopping the generation, let's insert additional users' inputs in the context using our cache blocks that we already have. So you can have additional cache block, insert those encoded users' inputs into that cache block, and on the next forward pass, you can insert that cache block in any point in the context, and that will allow the model to attend via attention to that part of the context and steer itself into changing the direction from generating Linux or bash script to whatever Windows uses. And to measure those kinds of scenarios, we use two benchmarks, one of which is Lost in Conversation. By the way, great paper. they introduce a, well, big challenge in modern LLMs that in different scenarios that are related to multi-turn reasoning, the performance of modern LLMs degrades, well, substantially. And we, well, took some of the samples, math samples they used to benchmark those models, which consist of shards of one task, which are complementary to each other, and you need all of them to solve the task successfully. And on the other hand, we've constructed ourselves a simpler setup where we have a math 500 dataset of math questions. We ask an LLM, well, like Gemini, something, to split one task into two parts, where one is not enough to solve it, and two shards are enough to actually solve this task correctly. And we insert those additional, well, you start with one shard, the first shard, and the model could not possibly solve this question, well, with the asterisks that it may have seen it in the training dataset. Well, and yeah, you insert one shard, then you wait a few decoding steps, so the model have time to generate something that can help it solve the task, well, in general, which may be relevant to the future generation or not. And then you insert that second or maybe following shards into the context in the same way, kind of simulating additional user inputs that are incoming after a certain amount of time. And you can see that for the math sharded dataset, you have, well, a lot of decoding steps, well, around 2,500 before the performance starts degrading, and that sometimes is caused just because model already have solved the, well, or have given you an answer, and you are trying to insert like the additional context into already finished generation. The same you can see, the same behavior you can see on the lost in conversation benchmark, while keep in mind that you have a lot more shards, so the time it takes for the model to receive all of them is much longer because, well, it receives the next shard every, well, 16 or 32 steps of generation. Yeah. I can show you the demo. Okay, that's a little bit slower than I've expected, but okay. So the idea is that you have a thinker, a writer, and sometimes they are asked to, well, continue generation of the writer or not. And sometimes it answers yes, and you can see the answer starting to appear. And that's basically the expected behavior. Beautiful music. Okay, so the idea is that, well, those blocks are arranged into, well, for thinker, it's, well, some question that I've asked, then the writer block, then the thinker block, and thinker can, well, reason upon the what is seen in the writer's output. And the writer sees thoughts as if it was its own thoughts and outputs the answer when the mode switching criteria answers yes to, well, continue the generation. Okay. Okay, yeah. I have a few other cases that I want to show you, which are here. Uh, this is one of the more recent papers. I actually don't really like this one that much. They show kind of strange results, which are not, well, I'm not sure how to, well, look at those, but the idea is, well, promising. This is the other direction of, well, LLM-efficient agents when you heavily interact with tools. So a lot of modern LLM agents use tools a lot. Those aforementioned speakers, for example, LSAI as well. Also, coding agents use tools a lot. And in real case scenarios, you usually wait for the tool call to be executed before launching the next one. And that is a big bottleneck for a lot of stuff in, well, kind of this LM efficient field. And the thing you want to achieve is to hide those tool calls behind the reasoning of the model itself. And the idea is very cool. They try to train the model to use it. So they use fine-tuning and then rely on some convoluted traces to, well, force the model to exhibit this behavior. The results are, on some benchmarks, are good. The models are around 3B size. And on the other benchmarks, the results are questionable. But the whole direction of tool call and hiding those behind the tool call execution, behind the reasoning traces, I think is, well, very promising. And yeah, will help to reduce the latencies a lot. Another paper is proactive LLM, which tries to, well, with additional training, and RL tries to make the model decide when to answer and when to listen in the scenario while the inputs are coming in real time, and they, well, probably may be long. So you can start generating answer before you have finished listening for the incoming query. They have a convoluted kind of pipeline, but the idea is that you have a streaming LLM which can start generating text with partial outputs while having positions shifted for the certain number of positions for the output start. And then they train the special head, which determines whether we should start, well, giving the answer, or we should wait for the additional user information that is still incoming. This is, by the way, really great direction as well, because it also reduces the latency between the user query and, well, model's output. But instead of hiding it behind the reasoning of the model itself, it hides it behind the user giving the query itself, so behind text recognition. Yeah. If you want, there are some links for other streaming, well, and those papers and works I think are related to the LM efficiency side of things. Yeah, I have a summary here. So the things I've talked today is parallel reasoning. Well, you can hide one reasoning trace behind the other, as the responsiveness, while you can hide the reasoning behind the generating the output. The tool call execution hiding behind the reasoning, and the also just mentioned the reasoning hidden behind the user incoming query, so text recognition. Yeah, I think that's all. I have a few QR codes here. One is for our reading group, where we discuss some papers once in 2 weeks. And the other is for our Yandex Research website. If you have any questions, please go ahead. Yeah, I think that's all. Thank you.
No questions? So I have a question myself. In the beginning of the presentation, there was a slide where you compared, I think, an accuracy of different number of engines. Yeah. Yeah, this. And I have very little about engines in LLMs, but how would you explain that the more engines are, the slower is conversions?
Okay, I see. The idea is as follows. You have 6 people writing in a shared Google Doc, and you spend a lot of time discussing who does what and what's happening. So you can probably spend around, well, a lot of tokens to discuss the idea. That's why, for example, they start slower at the beginning. And the convergence, I don't think that there is a convergence per se. So, but the idea is that they achieve the same levels of accuracy faster, but while spending some time discussing among each other the kind of best strategy to solve this task. Thank you for the question, by the way.